Welcome back, everyone. We are diving right into part 3 of our 5-part explainer series. If you joined us for the last explainer, we covered the absolutely crucial steps of proper collection and preservation. But now the real detective work begins. We are stepping into the lab to tackle the macroscopic physical examination of urine. And trust me, these initial physical clues give us immediate, massive diagnostic insights into everything from liver disease and glomerular bleeding all the way to inborn errors of metabolism. Let's get started. Here is our roadmap for today. We're going to prep our specimen, decode the vast spectrum of color and clarity, measure the physical density, and finally sniff out the underlying chemistry of odors. Section 1. Recap and specimen prep. Let's head straight to the lab bench. Like any good detective, we've got to prepare our evidence properly. Before we can evaluate a single thing, we absolutely need a uniform sample. So, you gently swirl the specimen to mix it up. This ensures any particulates that settled at the bottom are fully resuspended. Then, we transfer exactly 10 to 12 milliliters into a clear Cova tube. Now, you might be wondering, why that specific amount? Well, standardizing that exact volume ensures that when we eventually centrifuge the sample, the sediment volume is perfectly consistent, and that makes our microscopic cell counts mathematically reliable across every single patient.
Section 2, the spectrum of color. This is where things get really visually interesting.
Let's establish our baseline first. You always want to remember that urochrome is our main yellow pigment. It's actually excreted at a surprisingly constant rate, which is great because it provides a brilliant visual estimate of the patient's hydration. Pale yellow means dilute, dark yellow means highly concentrated. But there are a couple of other normal pigments hiding in there too. Keep an eye out for uroerythrin. That's what adds a pinkish, brick dust color to refrigerated amorphous uretes. Or you might see urobilin, which gives older, unpreserved specimens a distinct orange-brown tint, as the urobilinogen naturally oxidizes.
Okay, so that brings us to the massive array of abnormal colors you're going to encounter in the lab. If you have a dark amber specimen that produces a thick yellow foam when shaken, that is a massive red flag for bilirubin, pointing straight to liver issues like hepatitis. But you have to be careful here. Urinary pain medications like pyridium can also produce a thick orange urine with a yellow foam, easily tricking you into a false liver diagnosis. Moving down the spectrum, a shocking blue or green urine strongly suggests a Pseudomonas infection. If a specimen turns brown or black, that could indicate alkaptonuria, where homogentisic acid accumulates in alkaline urine, or it could even be melanin from a melanoma. And finally, a port wine color, that's a classic textbook indicator of porphyrins.
Now, here is an absolutely crucial clinical distinction, a classic trap you'll definitely see on exams. How do we differentiate red urine? Well, if you have a cloudy red urine, you are looking at hematuria. That means intact red blood cells are physically floating in the sample. But if you have a clear red urine, the cells have burst. You're dealing with hemoglobinuria from in vivo cell lysis or myoglobinuria from severe muscle breakdown. In the case of myoglobinuria, the patient's plasma will actually be clear, but their urine will have this clear reddish-brown hue. And hey, don't panic too quickly. A clear red urine might not be pathological at all. It could literally just mean the patient has a genetic disposition to excrete red pigment after eating beets, maybe they were snacking on black raspberries, or they're taking the tuberculosis drug rifampin.
Section 3, decoding urine clarity. Let's see how clarity builds right on top of those color findings.
By holding a clear container against a light source, we can visually grade its turbidity. We usually do this by placing text behind the tube and checking if the print gets blurred. And we grade this on a very specific scale. Clear means exactly that, no visual particulates. Hazy means there are a few particulates, but you can easily read the print right through it. Cloudy means the print is blurred. Turbid means the print cannot be seen at all. And milky means the specimen may actually be precipitating or clotted with fat or lymph fluid. Now, it's important to note that not all cloudiness is dangerous. Things like squamous epithelial cells or refrigerated precipitates can cause completely non-pathologic haziness. Interestingly, amorphous phosphates will create a white cloudiness in alkaline urine, while amorphous urates create a pink cloudiness in acidic urine. But you must recognize the dangerous culprits. Red blood cells, white blood cells, and bacteria are the most significant pathological causes for a cloudy tube. You might also find yeast, abnormal crystals, or trichomonads. And here is a wild fact. Trichomonads actually contain an esterase that can trigger a false positive on a chemical strip for white blood cells. So checking clarity isn't just some casual observation we jot down. It is a physical trigger.
Think about it. If the urine is yellow and perfectly clear, and the later chemical results are entirely negative, we often don't even need a microscopic exam. But any abnormal clarity results demand action. They dictate that we centrifuge the urine, pour off the supernatant, and get that sediment under the microscope to find out exactly what biological or chemical elements are causing the turbidity.
Section 4. Specific gravity and density. Time to get into the physical density of our specimen. Simply put, specific gravity evaluates the kidney's concentrating ability. We are comparing the density of our urine sample against the density of an equal volume of pure distilled water, which has a baseline specific gravity of exactly 1.000. This confirms if the specimen is concentrated enough to actually give us reliable chemical results later on. Normal random specimens usually range from 1.002 to 1.035. Honestly, anything below 1.002 might not even be urine. Normally, specific gravity tracks directly with color. Dark urine has a high specific gravity, pale urine has a low one. Makes sense, right? But there is one fascinating exception to this rule, and it's a huge exam alert: diabetes mellitus. In diabetes mellitus, which is caused by decreased insulin, you'll see a pale, dilute-looking urine that actually has a uniquely high specific gravity. Why? Because the massive amounts of heavy glucose molecules dumped into the urine add serious physical density. Contrast this with diabetes insipidus, caused by decreased ADH. That presents with pale urine and a very low specific gravity. So the magic baseline number to anchor in your mind for specific gravity is 1.010. Why that number? Because it precisely equals the specific gravity of the original plasma ultrafiltrate entering the glomerulus. We call this isotheneric. If it's lower than 1.010, it's hyposthenieric, meaning the kidneys actively diluted it. If it's higher, it's hypersthenieric, meaning the kidneys actively concentrated it. And keep in mind, the absolute maximum a human kidney can naturally concentrate urine is 1.040. One of our primary tools for measuring all this density is the refractometer. It measures the velocity and angle of light passing through just a single drop of urine on a prism. You calibrate it using distilled water to get that 1.000 baseline, or you can use 5% sodium chloride at 1.022 or 9% sucrose at 1.034. But here's the catch. If you use this specific device, you must mathematically correct your reading if the urine has heavy molecules. You actually have to subtract 0.003 for every gram per deciliter of protein and subtract 0.004 for every gram of glucose. Because of those heavy molecules skewing the physical density, we sometimes need advanced methods. Let's say you have non-pathologic large molecules, like radiographic IV contrast media from a recent scan, pushing your specific gravity abnormally high. In that case, you should use osmolality or reagent strips. Osmolality bypasses density entirely. It relies on the colligative property of freezing point depression to count the exact number of particles, completely ignoring their size. Reagent strips, on the other hand, use a bromthymol blue indicator to measure a pKa change of a polyelectrolyte. Just remember to mathematically add 0.005 to your result if the urine is highly alkaline, meaning a pH of 6.5 or higher. Both of these methods brilliantly bypass the false elevations caused by heavy glucose or IV contrast. Section 5. Odor and exam mnemonics. Let's wrap up our physical observations with the final sensory clue. Now, we don't routinely report odor on a typical lab sheet, but it is an incredible diagnostic tool. Lock this high-yield mnemonic into your brain right now: FAMOS. This covers the essential olfactory clues linking specific smells to serious systemic disorders. F is for fruity, caused by ketones in diabetes mellitus or starvation. M is for the mousy or musty smell of phenylketonuria. S is for the sweet maple syrup smell of maple syrup urine disease. A is for ammonia, which strongly indicates a very old specimen or a bacterial urinary tract infection, since bacteria convert urea into ammonia. And if you ever encounter a sample smelling intensely like sweaty feet, no joke, that is a rare, surprising indicator of isovaleric acidemia.
Section 6. Transition to clinical exam.
And with that, our physical detective work is complete. We've assessed hydration via urochrome, checked for liver disease with foam tests, graded clarity to trigger microscopic reviews, and accurately measured kidney concentration through specific gravity and colligative properties. But remember, this physical data is just the outer shell. When we finally introduce chemical reagents to this fluid, what invisible, potentially life-threatening secrets will instantly change color right before our eyes? Join us in the next explainer as we decode the entire chemical exam. You won't want to miss it.